to be in this slot here because people have already talked a lot about the importance of lunar volatiles. Nancy gave a great talk comparing what's at the lunar poles with Mercury. And we've heard Cubesats, and we've heard about AES program, and so I feel like I don't really have much to say other than this is going to be cool. This is, of course, on behalf of our science team and our engineering team, as Julie said, and this is a JPL-led project with Marshall involvement. You saw this exact same slide from Julie. We are going to be talking about lunar flashlight, of course, but we always have to say we have we've completed our non-advocate review of our science plan, and we're having our MCR-SR at the same time as NESF. Of course, why do we need to look for water ice? This is preaching to the choir. This is something where if you're going to have humans on the moon and you need water for drinking, breathing, rocket fuel, anything you want, it's much, much cheaper to live off the land than it is to bring everything with you. So this drives the strategic knowledge gap for the moon to understand the inventory of volatiles across the whole moon and their purity and their accessibility in particular. So one of the things that the ISRU people like to say is operationally useful quantities. So that means that it's like 0.5 weight percent where you can pick it up and extract it and use it. So that's what we're looking for here. Just a quick review, this is not what we're talking about, water inside lunar glasses. That exists. That's not operationally useful. It's very difficult to break those minerals down and use the water that's trapped inside. This is the M-cubed epoxy Cassini observation of possibly solar wind interactions or some other kind of very superficial interactions causing the formation of OH and possibly water as a superficial layer, also too little to be operationally useful to humans. Very, very interesting for science, don't get me wrong, not operationally useful for humans. And so what we're left with are these polar deposits that there's many, many lines of evidence for deep water deposits in permanently shadowed regions across both lunar poles, which could be possibly huge and a real useful resource for humans. We are not carrying a neutron detector. We're not going to be looking at those deep water stores. Instead, what we're looking for is water right at the surface. Could humans or their vehicles go into a permanently shadowed region and just scoop up the regolith and use what's at the surface to be able to extract water ice? There's some evidence for water frost in these permanently shadowed regions by multiple lines of evidence. I'm showing you two here that Paul Hain put together for us. So on the top here are locations where Diviner has shown these very, very cold temperatures. And down here is the Lola albedo, and you can see Lola albedo differences in there. And that's exactly the same thing that Nancy was talking about, where you have an enhanced reflectance from your laser altimeter, and that's consistent with, though not definitive of, water frost at the surface. So that's very intriguing. There's a couple other lines of evidence. LAMP also shows something that may be consistent with water frost. There are some albedo differences in lunar craters as well. So all of these point towards maybe there's water frost. It's not nearly as definitive as it is at Mercury, and it doesn't always line up with the neutron detection features at the moon, which are indicative of deep water stores. So we think these are probably two different processes in placing frost at the surface as opposed to the deep water. And so we're going for the water frost in this mission. Okay, so like I said, that drives out this strategic knowledge gap from the Moon First scenario, which you can get on the Strategic Knowledge Gap website, and that's understand the lunar resource potential, especially the composition, quantity, distribution, and form of water and other hydrogen species and other volatiles associated with lunar cold traps. Now, something I want to show you about this is that this is a very broad strategic knowledge gap. We're taking a very, very small bite out of it. Resource Prospector is taking another bite out of it. There's probably many, many missions to come that are going to address this. This is a huge problem interesting problem for science. It's something that for exploration we're going to need to explore in a lot of different ways. So this mission doesn't compete with Lunar Prospector, Resource Prospector. It's something that complements it, we hope, and complements a lot of missions to come. So what we're going to do is, this is the clever part, this is what got me on board with this mission, is we're going to use the solar sail. It's the same kind of configuration as what Julie showed you. But we're going to go into a large elliptical orbit around the moon. When we come around the South Pole and skim along the South Polar surface, we're going to gimbal that solar sail, and we're going to use it as a mirror. We're going to take the sunlight, bounce it off the solar sail into the permanently shadowed regions, and we're going to use a passive infrared spectrometer to collect the light from the permanently shadowed regions in wavelengths that are indicative of water frost. And I'll show you all of that in more detail. That's our measurement goal. And then we're going to repeat that measurement over multiple places on the moon, and that's our mapping goal. And the idea here is to be able to guide future rovers, future humans, and places that are going to be more amenable to having water frost, maybe have indications of water frost if they just want to be excavating the surface. And so you can combine that with the neutron data to say where the stores of water are. Okay, so again, this is very similar to what Julie showed you. It's a 6-cube Cubesat that's in position from it's imposed by the AES program and the SLS opportunity. The SLS opportunity gives us 11 CubeSats. They have to be 6U. That means we are not entertaining nanosats, small sats, explorer type opportunities. It has to be a 6U CubeSat. And we're using the same solar sail. That's one of the benefits of having these two projects very tightly coordinated, is we can share some of these development costs. So we have the same solar sails, about 80 square meters, and our infrared spectrometer. And you saw exactly the same thing, leverages solar sail development experience, CubeSat development and standards, and synergies between the two missions. So here's our flight system overview, just to give you a feel for it. This is the size roughly of your cereal box, right? It's 30 centimeters by 20 centimeters by 10 centimeters. Even I look tall when you look at this. So it's very, very small. One thing, it's not CubeSat philosophy in the sense that it's not modular, and they're not all off-the-shelf parts. It's not a really appropriate philosophy to take for deep space planetary missions that are going to do real scientifically relevant measurements. And so this is not all off-the-shelf parts, and it's not modular as you see here, but it does leverage a lot of CubeSat development that's gone on, especially the transponder and our radio that are being tested on INSPIRE, which is this interplanetary CubeSat coming out of JPL. So here's our solar sail volume. You can see that takes up about 1/3 of our volume, maybe a little bit more. So that's our biggest driver there, and that drives us down to a very small instrument. You saw on NESF that they've got a camera, we've got a 4-point spectrometer, but that's about all we can fit on this kind of mission. And we get a little bit better because we're closer. We get a kilobit per second downlink, and again, similar to NESF, we don't have a requirement for real-time data. We're not commanding in real time. Once we get into this orbit, it processes around the lunar pole. We get something like 60 orbits. We get what we get, and we can reconstruct that later. So we get as much as we can down, especially during our long loop out in our highly elliptical orbit, but we don't have to do it real time. I'm going to skip that. You can ask me about that if you want. Solar sail development history. Julie talked about this too. Solar sails have been proposed for many missions, and there's actually a NASA tech development mission for this mission called Sunjammer, which was just recently actually descoped to a ground test, but we should still be able to use the results of that. And then that same sail is going on these two missions. So our concept of operations, we separate from SLS in cislunar space, detumble, and start flying by the moon. We get captured into a low-energy capture orbit, and then we spiral down. And we spend about a year spiraling down, actually. So it's 6 months to get into our low-energy capture, and then it's about a year to spiral down. And that's just because we have almost no energy from the solar sail. There's just not a lot of energy to spend there. So we spiral down. We need to be something like 20 kilometers above the surface of the South Pole to be able to get enough signal to noise to measure what we're trying to measure. So we have that year spiraling down. We're hoping for on the order of 80 passes total, and then we will become an impactor like so many before us. What would I be as a NASA civil servant without a traceability matrix? So just showing you here again that these are what I'm going to talk about is science requirements flow from both human exploration goals and science goals. This is our level 1 requirement. Lunar flashlights have the capability to address a key strategic knowledge gap on the moon. And I would have to echo what Tony said before about Resource Prospector. This gives us a fair bit of latitude to address something that's important within the confines of this mission. It's not even Class D, it's the Class E or something like that. And so we have our measurement goal and our mapping goal, but we also have technology goals as well. So the fact of putting a solar sail onto a mission, the fact of getting into lunar orbit with a Cubesat, those are all really important things to human exploration and to NASA as a whole. So those are also our level 1 requirements. So I'm going to tell you about our measurement and mapping goals and our expectations. As I said before, we have a 4-point spectrometer. These are our bandwidths for now. These can be further optimized, and we are looking at that. But basically, so wavelength in microns from 0.5 to 2.5, and here's your reflectance. Here's your just lunar soils and Apollo lunar regolith at Apollo 16, and here's what pure ice would look like, and you can see these nice absorption bands due to the ice. Out here, of course, is the the water fundamental at 3 microns. We're investigating whether we can get that. We're not sure yet. There's noise in the detector, and we don't have an active cooling system. We just don't have room for it, and so this is a passively cooled detector. But we think we'll get good signal to noise at these 2 wavelength bands at approximately 1.5 and 2 microns, and then we'll take continuum as well. One of the things that we probably can't do is get absolute reflectance of the lunar surface. And so it's important for us to take these ratios of bands to each other in the absence of being able to pin these to absolute reflectance. So that's our plan, is to take A and B and do an A to B ratio, C and D and a C to D ratio, and then when you do those, you can plot them up and you can see A to B ratio, C to D ratio, here's dry regolith and here's water ice, so you can see a nice spread among these, and that's how you determine your abundance of water ice. Now this kind of modeling, this is what Paul Hain has really contributed to this mission, is this kind of modeling that's very dependent on your surface scattering properties, your assumption of the physical state of the water ice, the areal distribution of water ice. So we're in a sort of a wide parameter space here. But no matter where we end up, we're pretty confident that we're going to be able to distinguish water ice from dry regolith at about 0.5 weight% distributed aerially over our footprint. If we're lucky and we get good signal to noise, we're going to be able to distinguish water ice and regolith also from CO2 ice. Again, A to B bandwidth ratio, band ratio, C to D band ratio, and you can see these numbers are down here. If you plot them on the same plot, they're down here. So we'd be able to distinguish those 2 volatiles from each other if we're lucky. Okay, making that measurement is not trivial. We've never used a solar sail as a reflector, so the solar sail properties, of course, are really important. How much light is being reflected off the solar sail into the field of view of the instrument, into the illumination cone, depends on the material reflectance, how tight you can tension that solar sail, whether you can align all your solar sail panels together and focus that light, and of course the alignment of the solar sail with the field of view of the instrument. So that is being tested right now. I don't have the answer for you right now, but I'm going to show you as a function of our guesstimates that it's probably fine. The lunar surface, as I said, Paul Hain has done a bang-up job of doing this kind of modeling. I'm going to show you a little bit more about the instrument and about our navigation and our attitude control system, but all of those feed into how well you can make these measurements. And what we're aiming for is a 3 sigma confidence in the detection at the 2 micron band. So here's our instrument. For people who like instruments, forgive me if I stumble through this. This is not my kind of instrument. So we're looking once through 4 different filters and observing the same point on the surface with an off-axis parabola telescope. Here's the details of that. Like I said, we have a passively cooled design. Thanks. We have a passively cooled design. It's at -65 C, and we've had good suggestions about microcoolers and different kinds of detectors. We'll put those under trade study, but right now this is pretty much what we can do. And we may or may not have a small camera, may or may not be similar to the NESF Scout camera, and that'll help us understand where we've pointed the instrument and aid in the reconstruction. All right, I'm going to skip that. You can ask me about it, but we're pretty confident we can get the pointing we need out of our attitude control system. And the upshot of it is, here's our measurement prediction. Here's our here's our AB. Our A to B ratio is always going to be good. Here's our C to D ratio. And this says for reflected light off the solar sail, this is 5%, 10%, 15, 20, 25%. Okay, so we're down in the low tens of percents here. The fraction of observations with signal to noise over 3. Well, I'm sorry, this is over 1, over 2, and over 3 sigma. So over 3 sigma for these lower ones, we need maybe 20% reflectance of the solar sail. That doesn't seem like a lot to us. We thought, well, 20% of the photons getting down there is probably pretty good. But even if it doesn't meet that spec, we can probably get 2 and 1 sigma detections in the one band, and we're always going to be above that in this other band. So we think we're good there. We think that's very achievable. For mapping, we take what we can get. What we would like is 1 to 2 kilometers of footprint along the ground track. Our orbits, we just take what we can get, and of course, how close you are to the surface depends on the topography under you and the variation of your spacecraft. But here's our prediction spot diameter. So here's 1 kilometer spot diameter, and here's 2 kilometer spot diameter. The cumulative fraction of observations that are going to meet or exceed that. We see about 50% of our observations will meet about 1 kilometer spot size, 83 at 1.5, and nearly all of them at 2 kilometer spot size. So that's the expectation that we have for mapping. And we'll get a little less than 1% of the total lunar surface within 10% of the pole over 60 orbits. That's going to change a little bit as our system design gets locked down. So to sum up, it's a cost-constrained Cubesat mission to detect and map lunar surface ice. Oh, someone got it. Again, furthering maturity of CubeSats, which is something that we all as a community really want to do and understand whether these will be useful for future planetary missions. And yeah, so that was a picture that was sent to me recently that I just thought was cute and why we're interested in moon ice. It's probably going to taste good. Thank you.
Great. Okay, a few questions. Anybody have questions in the audience?
So, is it on? Did I miss it, or is there any other propulsion system in addition to the sails or RCS or?
Yeah, we have a cold gas ACS system.
Okay, all right.
I can't believe there aren't any other questions. Okay, there you go.
Hi, Amanda Cook. Just curious if you had to coat the sails with something else compared to the other mission, the previous one discussed. Yeah, the idea is to have them be as common as possible. They're already Kapton, which is already pretty reflective. To be able to do solar sail propulsion, you need to have pretty good reflectance to bounce those photons off. So we're not planning to make them different from each other. We're planning to take what we get.
I would think being this close to the sun and this close to the moon, you're going to have some odd thermal properties amongst this sail. Would you say a few words about it?
Yeah, it'll be hot and cold. No, you're right. I mean, thermal design is one of the things that drives any mission to the moon, obviously, and we've seen, you know, what happened with Chandrayaan, et cetera. And so we're very aware of the thermal constraints and the thermal design people are working hard at. I can't say much more. We do know it's a big driver.
Have a question over here in the back?
This is Shuai from Brown University. I feel confused about you use 1.9 micron band to detect water.
To detect ice.
To detect ice. But keep in mind that if you have piercing in that, it start drop, the reflection start drop at around 1.5 to 1.7. So if you just use one band, that can fool you.
Right.
And also if you have like a longer wavelength, that will give you thermal effects.
Right. So, well, there's probably not going to be a lot of thermal effect in 35K shadowed regions. So we probably don't have a huge thermal effect. We're not looking at lit regions. So we're not looking where natural sunlight is bouncing off and heating the surface. So we probably don't have a lot of thermal contribution Oh, this didn't move, did it? Yeah, sorry. Okay, well, I was going to show you the spectra, but yeah, you can talk to me later and I can show you. We're just using the Apollo 16 Highlands regolith, which doesn't have a marked pyroxene absorption. You're right that it might interfere, but we don't expect there to be large areas of pure pyroxene in these areas. We think that they're well-mixed lunar highlands type material, and they've probably been space weathered, and we're not expecting to see deep pyroxene absorptions.
Okay, thanks.
Okay, I have one last question, and then I know we have to move on. But I'm trying to imagine that solar sail folded up in that space that you're showing that you said is the size of our cereal boxes.
Yeah.
And then I'm trying to imagine it coming out. And how are you going to test it, or are you going to test it ahead of time? How does that
So yeah, that's an interesting question and something that I asked too. So it gets rolled up on this spindle. The material itself is very, very thin. Because you don't need it to be very thick in space, it's just going to be out there. But that makes it challenging to work with on the Earth and to be able to test it. The booms are inflatable booms actually, so they get filled up to make them rigid to hold the booms up. So everything does pack down. That part has been tested, and it unrolls and comes out just on its own. But it's very, very easy to tear. And so some of these calibration measurements that I was talking about, how reflective is it? Can you really hold this? We're not going to be able to test that fully on the ground. So we have a couple calibration maneuvers that we'll do in orbit. We'll pass we'll flash the Earth, and we'll measure the Earth flash, and then we'll also look at Jupiter and get our response that way.
Okay, thank you very much. Let's thank both of our speakers that we just had here.